Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 9. Solving two-point boundary value problems using shooting method. The shooting method is another numerical technique that can be applied to solve boundary value problems, typically for ordinary differential equations. The shooting method is useful for solving problems involving second-order or higher ordinary differential equations. It can be applied to many different types of boundary value problems. The shooting method is a powerful iterative approach for solving boundary value problems. The idea is to reduce the boundary value problem to an initial value problem. The ordinary differential equation is solved for an initial guess value of derivative, and the solution at the end of the interval is compared to the boundary condition. This way, the solution is refined for the initial conditions until the solution satisfies the boundary conditions. There are cases where a linear or nonlinear two-point boundary value problem is too complex or impractical to be solved by conventional numerical methods. These problems can be extremely difficult to solve numerically with conventional finite difference or finite volume methods. Boundary value problems involving a semi-infinite interval pose another numerical difficulty since one boundary is at infinity. Shooting methods for complex or nonlinear two-point boundary value problems offer great convenience and advantages to the numerical analyst. Consider the following two-point boundary value problems. These boundary value problems are good candidates for the shooting method. The nonlinearity is due to y prime and e to the x times y in the first equation. The right boundary in the second equation is at infinity. A boundary value problem of these type is generally treated as an initial value problem, which makes nonlinear ordinary differential equations easier to handle. Consider the following two-point boundary value problem subjected to Dirichlet boundary conditions, where P, Q, R, and F are continuous functions of x and defined on the interval from a to b, and Rx over Px is less than or equal to 0. Rearranging the boundary value problem, it may also be cast as follows. The boundary value problem can be reduced to a set of coupled first-order initial value problems by defining uppercase y1 equals y and uppercase y2 equals y prime, which can be expressed as follows. To solve the coupled first-order ordinary differential equations, uppercase y1a and uppercase y2a need to be known. Y prime a or uppercase y2a is undefined, so a suitable guess for the missing initial value must be made. A reasonable, smart guess can be deduced from the physics of the problem, or an arbitrary guess is assigned to uppercase y2a equals c1 to start the process. Solving the set of ordinary differential equation with uppercase y2a equals c1. With the first guess, the initial value problem is solved up to x equals b, using a suitable numerical method to solve the initial value problem. At the end of the first trial, the target value of uppercase y1, b equals yb equals uppercase b1 is recorded. This procedure is repeated for a second guess, uppercase y2a equals c2, and the target value is recorded. Uppercase y1b equals uppercase b2 equals yb. We continue shooting by adjusting the guess until the boundary value yb equals uppercase b is satisfied. In linear ODEs, the target values vary linearly with the guess values. Note that the estimated boundary values fall on a straight line. Using the results of the two trials, a straight line that passes through points C1, uppercase B1, and C2, uppercase B2, can be found to estimate the initial slope, y2a. A linear interpolation procedure leads to the following linear relationship, where C is the true initial slope. The true values of uppercase B and C depend on the accuracy, i.e., truncation and round-off errors, of the numerical procedure. To obtain highly accurate numerical estimates, the step size must be sufficiently small to ensure negligible truncation and round-off errors. Once uppercase B and C are obtained with sufficient accuracy, the numerical solution of the initial value problem is carried out one last time for uppercase Y2A equals C. A linear or nonlinear two-point boundary value problem may be given on a semi-infinite interval. Consider imposing the following boundary conditions on a boundary value problem, where the boundary at infinity is numerically achievable asymptotically. To handle this problem as a two-point boundary value problem, it is necessary to predict the proper value for infinity, which is not an easy task. But such problems are also convenient to treat as initial value problems using the shooting method. It is observed that the solutions approach their boundary, asymptotic values at different x values. If an estimate for x infinity is not possible, two trial solutions, with C1 and C2, must be obtained for a sufficiently large x value so that the solution has effectively reached its asymptotic behavior, but not so large that the solver becomes inaccurate or computationally expensive. Nonlinear boundary value problems can be converted into a set of coupled first-order initial value problems, just like linear boundary value problems. Finding the numerical solution for an initial slope is similar, but the CB relationship is no longer linear. We start out with two independent guesses for the initial slope, uppercase Y2 A equals C1 and uppercase Y2 A equals C2. The improved estimates are obtained as follows, where P denotes the iteration step. The advantages of the shooting method are: the shooting method can be easily implemented for both linear and nonlinear two-point boundary value problems. Numerical solutions of ordinary differential equations with an accuracy higher than second order can be obtained easily with either RK4, ABF4, or AMF4. The disadvantages of the shooting method are: a good estimate is required for the missing initial condition so that the iterative procedure converges quickly. High-order numerical schemes are susceptible to round-off errors. Nonlinear boundary value problems may lead to stability problems, especially over long intervals. In two-point nonlinear boundary value problems, the CB relationship is also nonlinear, and the secant method or root-finding methods may be used to estimate the initial conditions. Let us consider the following second-order two-point linear boundary value problem. We want to transform the given boundary value problem to an initial value problem and apply the shooting method to obtain an approximate solution. Then, we will compare our estimates with the given true solution. Setting uppercase Y1 equals Y and uppercase Y2 equals Y prime, giving uppercase Y2 prime equals y double prime, we transform the boundary value problem to a coupled first-order initial value problem as follows. We will use the RK4 with h equals 0.05 to solve the initial value problem using a guess for the initial value. See, for initial guess value of C1 equals 0, we obtain the right boundary value uppercase B1 as minus 0.293, 903, etc. For initial guess value of C2 equals 1, we obtain the right boundary value uppercase B2 as 0.695, 238, etc. Applying linear interpolation, we find the boundary value to be 0.2971, 2935. Finally, when we solve the following initial value problem with h equals 0.05 using RK4, we find a numerical solution that is accurate to 4 to 5 decimal places. With this note, we conclude this video lecture. That is all for now. See you next time with another topic. Bye.